Hi everyone, I'm Sophie from Carnegie Mellon University. I'm presenting our paper, Detecting Interpersonal Conflict in Issues and Code Review, Cross-Pollinating Open and Closed-Source Approaches. This is a collaboration between our Strudel lab and Google when I was an intern there. As a social technical activity, software development involves communication, such as issue discussions, code reviews, or mailing lists. However, these interactions are not always healthy. One study found that free and liberal open source software communities are such a rich source of insulting or profane speech data. Another study found that many people witnessed negative behaviors such as threats, harassment, and half of their respondents witnessed rudeness. Another study found that some communities neither reduce nor eliminate the negative feedback, as they believe it is core to their code review practice. But negative communication experience can be discouraging. I'm quoting from some GitHub contributors. One of them told us that negative reviews make one begin to question one's confidence. Or worse, they can make someone feel like they are done with contributing as much. More importantly, such negative experience is especially detrimental to marginalized groups, such as women and newcomers. Automatic detection can help with prevention and mitigation. There are already some qualitative studies on the nature of negative interactions, such as pushback, incivility, interpersonal conflicts, toxicity, and destructive criticism. But with automatic tools, we'll be able to flag or even rephrase the comments. Unhealthy communication isn't unique to software engineering. It has been broadly studied in other online communities. For example, Google's Jigsaw team developed the Perspective API to detect toxic comments. It is trained using New York Times comments. There are several tools for detecting toxic tweets. Convocate has a tool for detecting impolite comments and is trained using Wikipedia and Stack Exchange conversations. But off-the-shelf tools don't work well in software engineering. One study found that the off-the-shelf sentiment analysis tools have low agreement with software developers' labels. Some of the reasons include technical jargon, word contractions, emoticons, URLs, and code snippets. For example, support, error, and default have neutral polarity in the context of software engineering. Another example is that in real life, kill and execute might mean something similar, but it's not the case in software engineering. Therefore, kill the process is an ordinary command and is not coming from Queen of Hearts. There are several tools developed independently in software engineering. For example, a sentiment analysis tool for software engineering trained on Jira issue comments, another sentiment analysis tool on Gerrit code review, anger detector trained on Apache issues, toxicity detector trained on GitHub issues, and pushback detector trained with Google's internal code review conversations. Our work expands on the paper by Raman and colleagues, and the one by Eggleman and colleagues. There are several reasons why we chose these two works. At the time we conducted this work, these were the most recent works in this area. Also, they're different in several dimensions, such as across contexts. Raman's paper situates in open source, whereas Eggleman's situates in the corporate setting. Also across types of communication, Raman's paper works on issue discussions, whereas Eggleman's paper uses code review conversations. Therefore, our research questions are about how can we cross-pollinate the approaches in the two prior works across several axes and eventually see if they can benefit from each other and if we can combine them. More concretely, we cross-apply the two prior works along these axes. One is across the types of communication. Raman's work focuses on issue discussions, whereas Eggleman's work focuses on code review. Also across concepts. Raman's paper centers around the concept of toxicity, which is defined as a rude, disrespectful, or unreasonable comment that's likely to make someone leave a discussion. Whereas Eggleman's paper uses the concept of pushback, which is defined as the perception of unnecessary interpersonal conflict in code review, while a reviewer is blocking a change request. Also across contexts. Raman's paper works in the context of open source, whereas Eggleman's paper situates in a corporate setting. Also across methods. Raman's paper uses text-based features to build a classifier, whereas Eggleman's paper uses logs-based features, metadata, to build a classifier. I will discuss these features later in this presentation. Due to the time limit in this presentation, I will only go over some highlights of our results. For details and more results, please read our paper. It isn't easy to cross-apply these two prior works. There are several challenges. One is that we need to construct new datasets. Raman's work uses a dataset of open-source toxic issue comments. Because toxicity is rare, they used a set of heuristics to identify potential toxic issues and manually label them. The heuristics they used were issues logged as too heated or contained the keyword attitude. Using the same set of heuristics, we constructed a new dataset of open-source toxic code review comments. Now we can compare the two datasets across types of discussion. Eggleman's dataset consists of pushback and corporate code review comments. The way they collected data was to survey programmers to label code reviews from a stratified random sample and ask programmers to report code reviews they perceive as pushback. Using the same survey protocol, we surveyed thousands of GitHub contributors to construct a dataset of open-source pushback code review. Then we can link D3 and D4 across contexts. With the two new datasets, we can now cross-apply the two prior works across the axis I discussed earlier. Another challenge is the features. We calculated log-odds ratio of n-grams, meaning words or phrases, in both labels, toxic or non-toxic, or pushback or non-pushback. N-grams with a higher log-odds ratio in one label means that it is overly represented in that label than the other. This can inform our feature selection. We have some observations from the log-odds ratio analysis. First, we observed more second-person pronouns among toxic comments in the white rows. For example, you want, you think. Could you is overly represented among non-toxic ones, the green rows. But could you can be a polite phrase when expressing requests. Among the non-toxic code review comments, we see mostly technical terms, meaning that people focus more on the code. In the corporate setting, overall we see more technical terms. Both labels contain second-person pronoun-related n-grams. But among non-pushback corporate code review comments, we see more phrases expressing gratitude. Based on our analysis, in addition to the perspective API used by Raman, such as toxicity score and identity attack from the perspective API, we incorporated politeness strategies from ConvoKit. These include features such as second-person pronouns and gratitude. We also included a sentiment analysis tool trained using code review data. Eggleman's paper uses logs-based features. The first one is rounds of review. The second one is the active reviewing time, defined as time invested in providing feedback. The third one is the active shepherding time, defined as time spent on actively viewing, responding to reviewer comments, or working on the selected code review. However, we can't replicate all three metrics. We don't have access to active reviewing time, so we leave it out when classifying open source data. Also, Google has accurate measures for active shepherding time, but we can only approximate using walk clock time between the time when someone submits a pull request and the time this pull request is merged or closed. Now I'm going to present some result highlights. The plots I will be showing are precision recall curves. Intuitively, precision means how many comments classified as toxic are really toxic, and recall means how many toxic comments have we classified as toxic, meaning how many we have recalled. When applying the two prior works across types of communication, we applied the text-based classifier initially developed for open source toxic issue comments on open source toxic code review comments. The classifier with a bigger area under the curve has a better performance. Therefore, we see that the text-based classifier has a worse performance on our new dataset, the code reviewed comments. but overall, the performance is quite good. There are several reasons for the performance degradation. One can be that many of the code review comments are short and attached to a specific piece of code, which serves as the context for the comment, and without which we can't really fully understand the comment. Or maybe people just don't get as angry when reviewing codes as they are when discussing bugs. When applying across contexts, we apply the log-space classifier developed for corporate pushback code review comments on the open source pushback code review comments. Again, we see that the classifier has a worse performance on the new dataset, the open source pushback code review comments. There are also several possible reasons, but I think one of the most important reasons is that we can't replicate all three log-space metrics. We can't replicate active reviewing time, and the active shopping time is an approximation. Also, many open source maintainers are working as part-time, so there are some inevitable delays. When applying across methods, we apply the two classifiers on the same dataset. Here's the result of the open source toxic code review comments. We can see that the text-based classifier has a better performance than the log-based one, suggesting that toxicity is mainly about the use of inappropriate language. We also try to combine the features from the two classifiers. In this case, the combined classifier works better than the other two, suggesting potentials for combining methods. This is the result when we apply the two classifiers on the corporate pushback code reviews. We again see that the text-based classifier has a better performance. This suggests that although pushback was initially defined around the delay in reviews, there's more nuance in the use of language. When we tested out the combined classifier, we also performed a feature importance analysis. The x-axis is the impurity, which can be intuitively understood as the probability of an item being incorrectly classified if randomly assigned based on this feature. Features with higher impurity have higher importance. We can see that the top two most important features come from the perspective API. Together with other politeness features, text-based features are overall more important than the two logs-based ones. Some of the features are a little bit surprising. We would expect gratitude to be important, but it is among the least important ones. Also, note that the rankings of features are consistent in two types of conversations, suggesting some potential for generalizability of the methods. When detecting pushback, the most important features are the logs-based ones, and the text-based ones are less important overall. Now that I've talked about some highlights from our results, I'd like to talk about some implications. Our results, such as the consistency in feature importance rankings, suggest that there are lots of potentials to cross-pollinate approaches across axes. There are also many open questions. For example, why this performance degradation across types of communications and contexts? Also, when detecting pushback, the classifier's performance isn't great. So we probably need to improve the classifiers by maybe adding more features or using deep neural networks. We couldn't use state-of-the-art neural networks in this study because our datasets are too small. So we also have to expand the datasets by asking poor PhD students or people on Amazon NTurk, or using machine learning tools such as the weak supervised learning tool Snorkel developed by Stanford to automatically label more data. Also, there's a lot of work to be done on prevention. We also have implications on how to improve our communication experience. I'm quoting from one of our survey responses. Comments in text can be interpreted very differently from how the intention was, so always try to be extra polite when reviewing. Some of the things we can do include using fewer second-person pronouns and focusing more on the code, or showing more gratitude. In summary, in this work, we cross-pollinated two prior works across several axes. We overcame several challenges along the way, including datasets and features. We have several results on how the classifiers work across types of communication, context, methods, etc. These results have many implications on future research directions and open questions.